Hi everyone, welcome back to Math 261. This is Scott. Let's get started. Today, we'll be doing 4.2, in which we will revisit null spaces, column spaces, in the context of linear transformations. Null spaces, column spaces, and linear transformations. Alright, so first off, remember what it means to be a linear transformation. So recall a linear transformation is a mapping Sorry, the camera cut off there again, but it's a mapping between two vector spaces and before we said Rm and Rn, but we don't need to necessarily adhere to that anymore, because now we can more specifically look at vector spaces in the abstract. So we can say V and W such that one, if I did t of any scalar multiple of a vector v is equal to c t of v, and 2, t of any u plus v has to equal t of u plus t of v. And we write t maps from v to w like so, and we refer to and we call v the domain and w the codomain. Also, in the past, this has been called before the converse domain. Okay, so that's what it means to be a linear transformation. Now, in the context of Rn and Rm, we can always express these transformations as matrices. However, if we're talking about a more abstract situation, a more unusual vector space, then that might not be the case. But for every linear transformation, we can use it to define two different vector subspaces. And those vector subspaces will on the one hand be in V and on the other hand be in W. So for every linear transformation, we can define two vector subspaces. So there is, on the one hand, the kernel, as it's called. It's spelled like a kernel of corn, not like the military rank. So there's the kernel. So the kernel, which you can write KER of t if you want, but this is the subspace of V comprising all elements whose image under T is 0. It's the 0 vector of W. And in particular, if we wanted to write this, we could say KER of T is equal to the set of all V in V such that T of V equals 0, is what this means. Then there is also a subspace, the range. And this is a subspace not of V, but of W, of the codomain. So this is the subspace of W comprising all elements that are the image of some vector in V. And by image, I mean under T. So again, this is dressed up in finest math language, but it can be a little hard to understand exactly what is meant. So what this means is the range of T is equal to the set of all. Now it is W in W such that W equals T of V for some V in V. So it's all the outputs of the linear transformation. So let's give, as an example, something that is not within the typical scope of what we've talked about in this class, which has always involved columns and matrices and things like that. But let's take as an example, let's say that T is mapping from the space of polynomials to the space of polynomials. And in particular, let's say that T represents differentiation. So T of P of T gives you P prime of T. So this is differentiation. So just to describe this in words, T is the linear transformation that differentiates polynomials. So by differentiate here, I mean literally take the derivative. So for example, if I wanted to do T of, let's say 3t squared plus t minus 1. This would just mean literally taking the derivative. So this would be 6t plus 1. So just an ordinary power rule. Okay. Then what would the kernel of t be? Kernel of t. So that would be all of the polynomials whose derivatives were 0. So this is the space of polynomials whose derivatives are 0. Zero vector here means the zero polynomial means the number 0, the constant 0. So what is that? Whose derivatives equal 0? Well, notice here, nothing that had a t matches that description, only the constant terms. So in other words, this is, so kernel of t is the set of constant polynomials. Or you can say the space, because it is a vector space. Conversely, the range of t, this would be every polynomial that is the derivative of some other polynomial. So this is the space of polynomials which are the derivatives of other polynomials. So this is everything that you can get as the result of taking a derivative of another polynomial. Well, what kind of things can you get from taking other polynomials? Well, you can get any polynomial as the derivative of another polynomial. We can always anti-differentiate a polynomial. And so what this actually ends up being is the whole space. So the range of t is the entirety of p. So this is any polynomial. So in Math 252, you learned how to anti-differentiate things, and that's really what's going on here. It's every polynomial you can anti-differentiate, which is any polynomial. This is any polynomial. So the range of t equals just the space of polynomials all over again. Now, that's all well and good for something nice and abstract, and I'm sure you can imagine that such things would have a lot of uses, for example, in Math 256, and you'd be right. They certainly do. However, this class is more focused on the case of Rn, Rm, things like that. So here we can make all linear transformations into matrix transformations by the recipe actually that was spelled out at the end of chapter 2. So here, our focus is going to be on matrix transformations. So matrix transformations, and this is a case where the dimensions are prescribed in advance. So in the case of polynomials, we didn't set in that case any cap on the degree, and so as a result, we ended up with what is called an infinite dimensional vector space. But more on that later on in the course. Here, though, the dimensions are fixed in stone. So let's say that A is m by n, and T, which is the transformation from Rn, that's R November to R Mike, is given by T of x equals ax. So this is a species of linear transformations. It's quite regular, quite well understood, and you'll understand it all too by the end of this term. But let's discuss what the kernel of this would be. So the kernel of T, this would be equal to the set of all vectors in Rn whose images under T are equal to 0. So this is the set of all V in Rn such that T of V equals the 0 vector. And it's the 0 vector of Rm. But this is also known as the null space. This is the same thing as the null space. So null space of T is equal to, or actually of A, I should say null space of A, is equal to the kernel of T. Null space, we talk about that for matrices. Kernel, we talk about that for transformations in general. And if you'll recall, if we wanted to find a basis for the null space, we could do so by setting up the augmented matrix, etc., according to the recipe laid out in chapter 2. Okay, now as for the range of T, this is the set of all W in Rm such that T of V equals W for some V. In V, actually I should say this is for some V in Rn. So these are elements of Rm, R mic. So this, but this is the same as the column space. So that means column space of A is equal to the range of T. All right. Now note, an important note here. Note that the column space and the null space come from different vector spaces. They are different sizes. So the null space, so elements of the null space, these are elements, so these are elements of Rn. So that means they have n entries. And elements of the column space, on the other hand, are in Rm, that's R mic, they have m entries. So they're not the same number of entries. So the null space and the column space are they are made up of vectors of different sizes. So null space vectors are the same as n, which is the number of columns of the original matrix, whereas the column space, those are elements of Rm, so that's the number of rows of the original space. Let's see, so one thing though that this can enable us to do is it enables us to immediately conclude that something is a vector space if we can show it to be a null space or a column space. So this gives a way to show that a certain set is a vector space. And that is to show that it is a column space or a null space of a known matrix. So show that it is either the column space or the null space of a known matrix. And here's how we could do that. So for example, show that the following is a vector space. So here we have a set, and the set is going to be made up of vectors of the form A, B, C, where we are going to be given some relations between the A, B, and the C. And the A, B, and C will be given with some equations such as A plus B equals C, C minus 2A is equal to 0, and then finally, let's say A plus B equals 0. I would say 2A plus B equals 0. Okay. Now the question is this manifestly the null space or the column space of any matrix? Well, looking at these equations over here, this looks like a system of equations. And so, if we can rewrite it as a homogeneous system of equations, so that looks like that, minus 2a plus c equals 0, and I'll write it even in standard form with all the entries nice and lined up, and 2a plus b equals 0. So this is a homogeneous system of equations, and a homogeneous system of equations, its solution set will be the same as a null space. So this is a homogeneous system of equations. So in other words, the solution set is the null space of A, which equals, and then here would just be the coefficients of the A, B, and C. So it'd be 1, 1, negative 1, negative 2, 0, 1, and 2, 1, 0. And let's say we wanted to find the basis for this. So as a follow-up, so let's say B, find, let's say A basis. Shouldn't say the basis because there might be more, because there is more than one choice of a basis. Find a basis for W. So the way you find a basis for the null space of A is you set up the augmented matrix 1, 1, negative 1, negative 2, 0, 1, 2, 1, 0, the augmented matrix with the zeros. So that represents the system of equations that we see right up here. And then we would just row reduce it. So here we can see that that we can clear away everything below this 1. Now some of you like to get very fancy with your row reduction, but you don't have to get very fancy, and it's not so hard. You just you can just take the pivot and use it where you need to use it. So I can clear out row 2 and row 3 just using that pivot. Some of you like to get fancy and add those and do stuff here and there and everywhere, and that's fine. No harm in that really, but it's also not really. It's not really necessary to get too creative. You can just use a pivot and you can use it like a hammer. So I'm going to use row 1 here. I'm going to do 2 times row 1 plus row 2. So that's going to give me 1, 1, negative 1, 0, 0, 2. 2 times row 1 is going to make negative 2, so negative 1, and then 0. And then here, 2 times row 1, negative 2 times row 1 plus row 3 is going to be 0, negative 1, and then negative 2 is going to make 2. There we go. So there's that, and then I will clear this. I use this to clear up above, and so that's going to give me I'm going to switch this up to here, and I'm also going to use it to clear everything away. So notice I'm getting a little bit less explicit in my row operations because I've gotten a bit more practice at it. Changed my mind here about how I want to write that. So now I'm going to, as I said, make it 0, 1, negative 2. So I'm going to scale it and move it and use it to clear away everything. So upstairs, I can get that by taking the original one and adding it. So you don't necessarily need to show everything about this, just as long as at every stage what you are writing is in fact row equivalent, that's good enough for us. And then clearing that one, it's going to be added 2 times it, so it's going to be 0, and then that's going to be 0, and then that's going to be 4 plus negative 1 is going to be 3. And then notice that will become a 1 when we scale it down, and I can use it to clear up everything. And so I'm going to get 1, 0, 0, 0, 1, 0, 0, 0, 1. And so what we actually have here is the trivial null space. So the null space comes from there being free variables. So there are no free variables, which implies that the null space is the trivial subspace. So null space of A is equal to the vector 0. So there is no basis. So trivial subspaces do not have bases. So this is what you can do if if you're trying to show that a space that is defined by means of equations is in fact a vector space. And the other direction is where the set is defined in this manner. So let's say W is equal to let's say A minus B, and then 2B, and then 3A, where A and B are real numbers. So let's say A, show that W is a vector space. Well, here we can try to find the columns that this is the span of. So if I take the little elements of W, now here I'm going to write them with W. In the previous section I wrote them with A. It doesn't matter though. So those are things of this form: A minus B, 2B, 3A. But that's the same thing as saying A0, 3A plus negative B, 2B, and 0, which is the same as saying 103, negative 1, 2, 0, with an A in front of this one and a B in front of this one. Which means this is the same as 103, negative 1, 2, 0 times AB. So what this means is, since A and B are totally free here, that W is the column space of A, which is 103, negative 1, 2, and 0. And then B follow-up would be find a basis for W. So same old follow-up. So once you have been asked to show that something is a vector space, a frequent follow-up would be find a basis. Find a basis for it. Well, the basis for a column space, we find that, if you'll recall, by taking the matrix A, row reducing, and looking for where the pivots are. So So A is equal to, and here we do not need to augment it or anything like that. We just put this 103 negative 1 2 0, and we would just row reduce and find the pivots. So here, this is clearly going to clear out that, and then clearly it's not going to clear out that, or down there, so we're going to end up with pivots in every column. So pivots in every column, and what that means is, thus the two columns of A originally are a basis. So each variable is basic, no free variables, which means that each of the variables of A will go into the basis. So the basis B will be 103, negative 1, 2, and 0. So both original columns belong to the basis. So basic variable means that column of the original matrix belongs to the basis. All right. Now, if there are any stray constant terms floating around, just as in the last section, that's usually an indication that the thing in question is not a vector space, and you should not try to use these techniques to demonstrate that. So, sets defined with stray constant terms are usually not vector spaces. So don't try to use this. Instead demonstrate that fact by checking whether 0 belongs to it, just as in the previous section. So as in previous section, demonstrate this by finding a failure of a necessary property and usually, so this is more like a tip to you, usually 0 will not belong to W. So that's what you usually want to look out for. Check that 0 does not fit the format of W. Alright, and now there's one last twist on the column space and the vector space and things like that. And that's something that we can introduce right now. We're not going to look at the most important facts about it, but there's no harm in introducing it. And that is what is called the row space. The row space. So if we have a matrix A, the rows can also be a vector space, and we would typically write those as row vectors. So this is the space spanned by the row vectors from the rows of A. Row vectors can either be written horizontally or vertically, it doesn't really matter. Horizontally, so that would look like something like this, 0, 2, -1 would be the usual way we would write that. Or vertically. Doesn't really matter. A vector is a vector, whichever way you write it. So the row space will be a subspace of, and if you think about it, how many entries are in each row, it'll be however many columns there are. So if A is m by n, then this will be a subspace of Rn. And because it's a span, that makes it ipso facto automatically a subspace. So we don't even need to worry about anything, prove anything. This is just a stray observation about something that will become a closer friend of ours later on. But for now, I'm going to leave it at that and call that a section. So join me for the next episode of Math 261, where we will look more into the matter of linear independence and bases. So until then, bye.